Hello everyone, welcome to the second reinforcement learning lecture, where we will be going more in depth on various advanced deep learning topics. We'll start off with deep QLearning, which is a very interesting, more basic reinforcement learning technique, and see how it is used in deep reinforcement learning. Then we'll be talking about actor critic, which is basically a variance reduction method for policy gradients like reinforce. Finally, we're discussing world models, which fall into the wider umbrella of model-based reinforcement learning problems. World models is a very exciting and active field of research that takes in loads of different areas of deep learning and combines them all together. That's exciting stuff. Let's first start with a recap of the last lecture. In the last lecture, we introduced reinforce, the most basic method for deep reinforcement learning. In reinforce, we sample first a trajectory, which is a sequence of state, action, reward, state, action, reward, so like a rollout of your game. Using this trajectory, we update the parameters of our policy network. So the trajectory is sampled from a distribution that is parameterized by theta. And why is this? It's because we act using the current policy by theta. So what we want to do is we want to learn the parameters of this policy network. So the parameters theta, because this policy pi is a neural network that basically predicts what actions to take. To update the parameters of reinforce, what we do is we update based on gradient ascent, and we reinforce, so we increase the probability of actions that have high reward to go. So that's this GT. This GT basically says how much reward did we get after taking the action, and then properly discounted as well. Be sure that this GT is going to be very important in this lecture, so we're going to use this a lot. But first we're going to make the notation a little bit easier to work with. So we're going to be removing all the time-based indices. So instead of saying RT, so the reward at time step t, we're just going to use R. Instead of using X and T, we're just going to use action A, and state T at time step t, we're just going to use state, etc. Also for GT. And for the next time step, so the reward at t plus 1, we'll just be using r prime, and the action at t plus 1, times at t plus 1, we'll be using a prime, etc. And let's introduce a very important concept within deep QLearning, namely the Q function, which is, as you could have guessed, what it's based on. The Q function is also called the state action value function. This because it gives the expected value, so the value function, of taking an action in a state. So it's an expectation over the discounted reward to go after taking an action in the state. There is one more very, very important thing to mention about the Q function. And it's so important that I will reiterate it many times, if I don't forget it, which is that the Q function is specific to a policy. So as you can see, the Q function has this pi up there. So a Q function is specific to a policy. So why is it specific to a policy? It's because you take an action in a state, and after that, you're going to be executing your policy. And then we're going to see, okay, what is the discount reward to go that we expect after taking that action and then executing that policy. So if you would be computing the Q function for another policy, it will be looking very different because you would be doing different things after taking that action in the state. Cool thing about Q functions is that we can talk about the optimal Q function. The optimal queue function is a queue function that maximizes the policy. Or basically, the optimal queue function is the queue function for which the policy is the best. So it gets the highest expected value. So it's basically saying choose the policy that maximizes the state action value function. So why is this? It's basically saying if we have a policy that is not that does not have the optimal queue function, then we can find another policy that is going to get better rewards than expectation. And given this optimal queue function, we can actually also, the other way around, derive the optimal policy. Because if we know what the optimal queue function is, what the best expected value is that we can get in a state given an action, then we can just very easily derive a policy from that. We can just say, the best policy is to take the action that maximizes the optimal queue function. So this is basically a deterministic policy that always does the same thing. This policy always selects the action that maximizes the value of the optimal queue function. So why is it so useful? This means that if we can derive what the optimal queue function is, then we can also derive what the optimal policy is. So knowing how to find the optimal queue function can be turned into taking actions. We'll be going into a bit more mathematical section here. Be aware that we are not going to be asking very hard questions about this in the exam, so don't worry if you cannot fully follow it. Next, we're going to discuss how we can compute the reward to go G recursively, which basically means that G is a function of state and actions. So how can we compute this based on itself, namely the reward in the next time step? This is actually very easy. Let's get into it. So we have this G, and we know that it is basically the reward in the next step, plus the reward in the step after, etc., which are then discounted in a certain way. We can basically extract a single discount factor, gamma, from this whole equation. And now, if we look at this equation, see that this is still a sum. This is a sum over time steps, but t prime, but now starting one time step later at t plus 1 instead of t. So again, we see this very familiar term right here. This term is actually precisely equal to the discount reward in the next time step, t prime. So this might be a lot of terms, but if you look at it with a lot of patience, you can clearly see that it's really easy to rewrite this discount reward to go using itself. So what does it basically say? It basically says that the discount reward to go is equal to the reward to go, the discount reward to go is equal to the reward in the next state plus the discount reward to go in the next state. So we have this very nice recursive computation here. Next, we'll be looking how we can compute the discount reward to go recursively, which basically means writing it in terms of itself. We can write out the discount reward to go like this. The reward in the next step plus the discounted rewards after that. So we compute the sum of all these rewards and then properly discount them. What we did here is actually we extracted a single gamma term. So this way, this gamma distributes over all the terms here. And now if we look inside these braces, we see that this is a sum as well. It starts a term later, namely at t plus 1 instead of t, and then computes the discount reward to go there. This is actually a very familiar sum over here, because this is equal to the discount reward to go in the next step, g prime. So if you can completely follow that, look patiently at the definition of discount reward to go, then see how you can extract this gamma, rewrite this sum as a simple sum using the sigma notation, and then this is equal to the discount reward to go one time step later. This gives us this very nice recursive computation, which basically says the discount reward to go is equal to the reward in the next state plus a discounted plus a single discount, and then again the discount reward to go in the next state. So we're going to use this recursion to derive more about the Q function, in particular the optimal Q function. So we get this definition for the optimal Q function, namely that it is the Q function, which is the definition of the Q function, for which the policy is best. So basically it uses the best policy, and then you compute the expectation over the discount reward to go. And again, like I said, is the expectation of taking an action in a state and afterwards following the policy pi, so the optimal policy. So we can say we take an action in a state and then not just follow the policy that maximizes it, but the optimal policy, so p star. And what we also did here is that we expanded the discount reward to go using this recursive trick that we just derived. So instead of using g, we'll be using reward in the next state plus the discounted g prime. This is going to be equal to the optimal Q value, or also the Q value of the optimal policy. So we can also expand this expectation. Why? That is because this reward does not actually depend on anything else but taking that action in the state, because it's the immediate thing that happens after taking the action in the state, and the policy, which is used after taking the action in the state, is not going to be important for what is the result of taking that of that reward. So the idea here is that this reward only happens immediately after taking the action in the state and is furthermore independent of the policy. So we can split up this expectation by first only sampling the next state and the next reward, and then we get this reward in the next state. So we first only do what happens immediately, namely taking the next state and the next reward. And then we can actually see this g prime is now going to be an expectation of your trajectory that happens after executing the policy in the next state. So this is maybe a little bit hard to follow if you have not worked with expectations before, and we're going to be asking very important questions, but the idea here is that you can recursively compute this Q function as well, and this reward is independent of the rest of the policy. So we don't need to have it conditioned on the policy. We can also expand again this term over here. So we can say, the first thing that happens when you take the trajectory when you sample a trajectory with a current policy is that we are first going to sample the action using this policy, right? That's the first thing that happens. If you look at the trajectory, that's basically a very sequential thing. The first thing that happens in a state is that you sample an action there. So we first sample an action from the optimal policy, and then we're going to see what happens when we take this action in that state, given, and then executing the current policy, namely the optimal policy. And if you remember correctly, it's actually right here. This looks exactly like the Q function. So we find a very nice recursive computation for the optimal Q function. Namely, we can just substitute here the optimal Q function, Q star of S prime A prime, so the Q function in the next state. And then we have this very nice recursive computation, where we first sample the state and the reward in the first, from the first state in action to get the next reward, and the next state as well. And then we estimate we compute the discounted reward to go in the next state by taking first an action from the optimal policy and computing then what's the Q value of the optimal policy in that state if you take that action. Now we can simplify this even more. Why is this? We derived before that the optimal policy, B star, is equal to the policy that always takes the action that maximizes the optimal Q function. And so we can basically just say, instead of taking expectation over this optimal policy, we can just also say the expectation of the optimal policy, that's not actually an expectation because it is always due to the same action. So this is actually not really an expectation because it always due to the same action. So we can deterministically assign this to the action it uses, namely the action that maximizes this Q function. So we can simplify this expectation over the optimal policy by just taking the action that maximizes the optimal policy. And why is this so interesting? It turns out that in this equation, if you look closely, there is not a single mention of pi anywhere. So we don't actually ever need any kind of explicit policy to compute this recursion. This recursion always happens. So the optimal Q function is always going to be equal to this recursion, where you first sample a state and a reward in the next state, and then you compute the sum of this reward in the next state plus discounted the discounted maximum of its optimal Q function, where you maximize over the actions taken in the next state. This recursion is very important. If you could not completely follow the derivation, that's fine. But this optimal Q function is going to be very important and very fundamental within reinforcement learning. So why is this recursion so useful? It basically means that we can test if we have an optimal Q function. Namely, if we have a function that exactly follows this recursion, then we know that it is the optimal Q function. And if we're looking for functions, then, well, the obvious thing is to think about, can we find this function using neural networks? So that's the idea here. We want to find this optimal Q function because it allows us to derive a very strong, or basically the optimal policy. So to find this optimal Q function, why not try to use a neural network that estimates this optimal Q function? That's what we're going to do. We use a neural network, Q theta, that's going to estimate this optimal Q function. And from this we can derive a very good policy, namely just a policy that always takes the best action from this estimated Q function using the neural network. So just like you would do with the optimal policy. So how does a function like that look like? It's actually very easy because it's pretty much like the policy network that we use within reinforce. The only difference is that instead of taking a softmax output, because you only want to use a single output and you want to get distribution over outputs or over actions, what you now do is actually you don't have any activation function in the loss layer. So you just use a linear output. And that way, for every action, you're going to get a value. So in the output layer, you will get for every action, given a state, what the expected Q value is for that action. So we just use a linear output layer instead of a softmax or something else output layer. Let's return to the equation of the optimal Q function. What we can do here is that we can simply, we just move this thing to the left. So we just subtract everything with this large term over here and move it to the left. So we now see that we can also say that the optimal Q function is a function for its Q function minus this big expectations equal to 0, right? And this gives us a very convenient way, because it's a difference that we can just minimize, right? So we often call this the Bootstrap error or the Bellman error. Both mean the same thing. So we want to find a neural network such that this difference is almost going to be 0. And minimizing a difference is basically a regression problem, right? So what we do is we're going to try to find the parameters theta that minimizes this difference. In this case, we're going to use a squared difference. So we compute the Q value in the current state, an action, and we subtract this expectation. So you take the reward in the next state and you add the discounted maximum of the Q value in the next state. Note here that you also use a parameter theta here. So you use a parameter theta both here and here. So we can actually just compute this using a neural network. And so how is this a regression? So you can kind of say that this is a prediction. So we predict that the Q value of this state in action is going to be, this value. And then we check it with the target, which is this other value. So we're going to see, okay, well, how close are they? How can we regress them together? How can we minimize that difference? So look at it in a bit more like a sequential fashion, so you can really follow the steps. So we start off in a state and an action, and we have some parameters theta, and so we're going to get a prediction for this state and this action. So we use the state and the action and the parameters theta to find a prediction, Q theta of SA. Then we're going to execute the action in the real environment. So we're going to say, sample for me a reward in a state, using this action in the state, and then we get a next action and a next reward. This all happens using the normal MDP sampling procedure that we discussed many times before. Using this state, we can actually compute what is the best action to take in that state. And then we can find this discounted Q function using just the same parameters theta of your neural network. Right, so this is a very easy, simple thing. So this Q function is based on the first state, and this Q function that takes the maximum over actions is based on the second state. This can be added together with the reward that we get in the next state. We add this together to get the target, and we do a squared error to find finally the bootstrap error that we minimize. These are the steps that happen during deep QLearning. Now let's look at the deep QLearning algorithm. We start from state S, and then we're going to loop from this state. First, what we do, we're just going to follow what the computation graph that we just showed. So we're just going to take an action in that state. And how we're going to do this? We're going to choose the action that maximizes the Q function that we have estimated. So Q theta of SA. Next, of course, we just execute that action in the environment. That gives us a new state and a new reward. Given the result, we update our parameters. So we say, we want to do a gradient descent step because we want to minimize the error, not maximize it. I'm going to be computing an estimate of this bootstrap error that we discussed. So we're going to be computing the gradient. So we're going to want to minimize the difference of what a neural network predicts minus the target, which is basically this reward in the next state minus this discounted this discounted estimate of our Q function in the next state. And then we just move to the next state and loop again. So the main interesting thing here is first this bootstrap error, which is based on this optimal Q function. And also, one interesting thing is that unlike in reinforce, this is an online algorithm because we don't need to compute the full trajectory and then update. We update after taking each action. Right? We take an action, we don't update, we go back, we take an action, we don't update, etc. So this is, in reinforcement terms, an online algorithm. There's one problem with this algorithm, which is that we always take the same action while we execute this, right? Because we select just the action that maximizes this Q function, the estimated Q function. But is that such a good idea? Well, not really. Why is this? It's basically saying like this. We want to learn, for example, how are we going to find out what's the best restaurant in our city? And how would we do this? Would we do this by always going to the same restaurant that looks pretty good? No, we wouldn't, because we would never explore and find out new things, new restaurants. We would never find anything better than the restaurant that just looks kind of good in the first glance. So, what we need to do is that we need to explore a bit more. Because with this kind of action selection, we always just take the maximum. That's very deterministic, never explore. We only exploit that we know that some things are pretty good. A very simple solution to this is called epsilon greedy. Basically what we do is we just take a random action with epsilon probability. So instead of just taking the best action, you always take the best action, but with epsilon probability, you just take a random action to be able to explore a bit. This is not by no means the best way to explore. There are way smarter algorithms, but it's a good baseline to start with. There is another problem with this setting, which is that both the prediction and the target are dependent on your parameters. So if again we look backwards through our graph, like we also did in the last lecture, we see that there are multiple paths to theta. Namely, to our prediction, which is of course what we want. We want to make sure that our prediction is right. But it's also happening through the target So our target is actually also dependent on theta, because the target uses this Q function in the next state. So that seems weird, right? And indeed, it is pretty weird and pretty wrong. So what happens if you try to train it is that it just goes everywhere and basically keeps competing with itself because there's no clear defined target, because you change your target when you're training. So this doesn't really work. So what's the solution? Basically the same as in the last lecture. We just say that this line is actually not a differentiable line. So we use this dtext grad, this operation in Python is called dtext, to remove the gradient from this line. And now we have actually a much more stable algorithm. This helps quite a bit. It's not perfect, but it helps a bit. So now we get a new version of our deep QLearning algorithm. Instead of always taking the same action, we now do epsilon greedy. So we take a random action, the epsilon probability. That's over here. And in the update, we now add this weird turnstile bot symbol to detect the target from our graph. These two modifications significantly help deep QLearning converge and train stably. However, it's still not that great. There are many things to get tricks to get this working. The most important one is experience replay. It's basically that you batch together multiple experiences, multiple trajectories, or not trajectories, but transitions together, and that you take the average over that. So it's basically like batching and keeping track of what you already have seen. And there are other very interesting things: target networks, double QLearning, modular returns, gradient clipping, all very interesting. You can actually explore these in the assignment 5C, that is on reinforcement learning. You can explore some of these and see which ones help to get this all working. So to summarize deep QLearning, we estimate the optimal Q function, which we defined using this very nice recursion. This allows us to minimize this bootstrap error. However, deep QLearning is not that easy to get working. It requires many annoying tricks, so you will have to implement that if you really want to get it working. Next, we're going to look at active critical algorithms, which actually combines some of the ideas from QLearning with policy gradients.